Good morning, everyone, and welcome back to day 6 of Pixelpalooza. We are so glad to see so many of you that have come back to join us for this exciting session where we'll be doing more of a deep dive into the more technical aspects of Pixeltope as a virtual production solution. The topic of today is going to focus heavily on optimization, performance, and technical aspects of the engine. We're going to be doing a brief look at look dev, lighting, reflections, and then we're going to move on to performance, profiling, and how to ensure that we hit our target frame rates. As always, please note that we have 3 feeds here in our webinar layout. There's of course my webcam interface, so you can see my handsome face. Over on the side here, we have the screen share as well as our live SDI output feed, which is being converted to a webcam feed. The reason we have it output that way is, as you all know, since everyone's working from home these days, we have some issues with bandwidth. So hopefully the webcam feed on the side, when we are going to be showing live output feed from the engine, it's going to give us a smoother viewing experience. And then down below, we have the actual direct screen share from my left monitor, which is going to be a bit more lag intensive, but hopefully also a bit higher resolution. Please note that if you have any issues with the video quality, if things end up being too blurry to really be watchable, please rest assured that we will be making, as always, all the recordings available after this session. So you'll be able to review all this material at your own pace after we have finished here during this live session. My name is Frank Daniel Moenvevik. I'm a product specialist at the Future Group, where I've been for the last 3 years. Enough about that. So we are going to start today off with a cursory glance at the Pixeltope render pipeline and what implications it has for our performance. We're going to move on to some look dev. We're going to look at best practices in terms of lights, baking lights, as well as setting up reflections. We are going to then transition over to ray tracing, video playback, and finally wrap it up with a practical use case of optimizing a poorly performing set. So on that note, let's dive right into it and take a look at the Pixeltope render pipeline. So we have Pixeltope up and running here in the background. So let's just go ahead and fire up a level. I think for now, I'm just going to go ahead and open up our level, the studio level, which we see down here. Let's just start it so I can find it. Let's go ahead and launch it in Editor. So we've talked a lot about our render pipeline. We talked about how we efficiently inject video into Unreal, how we're able to cleanly composite it with our Unreal graphics in order to get a final clean output image. But we haven't really talked about the implications this pipeline has. Let me just go ahead and get rid of these spheres, which are cluttering my scene, which we're going to be talking about later, but not right now. That's going to be down here under, there we go. Let me also go ahead and position my talent. We've been fiddling a bit with our cameras, so I just need to ensure things are looking nice and lined up. Let's just go ahead and grab our camera root as well as our comp plane and move that in. There we go. And at that note, we are good to go. So in terms of performance, we of course have a frame budget that we never, ever can surpass. If you're doing a 60 FPS production, that means you have a bit over 16.6 milliseconds per frame. If you're doing a 50 FPS production, that means you have a slightly higher budget of 20 milliseconds per frame. This is a hard limit that you should never, ever be crossing. Now, it's fairly easy to profile different aspects of what's happening within Pixeltope. Let me just go ahead and clean up my key a little bit. That'll do. We've previously looked at our optimization tab, where we can easily see what's happening with our frame rate. We can easily see what's happening with our different draw threads, whether we are bottlenecked with CPU, GPU, or GPU. We can see by hitting Control Shift comma, we can bring in a profile GPU window, which shows us an exact breakdown of what's happening in any given frame. But there are situations where, especially if you're using a lot of input streams through Aira, for instance, if you have 4 or 5 media input streams through SDI, you might start missing your target frame rate counts despite everything looking fine and dandy within Pixeltope. That is the first thing we're going to look at today, what that is and how we can identify it. Also, just to make sure everybody knows, if there are anything that is unclear during the seminar, if you have any questions or things you want to ask, whether it's on topic or not, please do not hesitate to ask questions. We have our team of engineers and artists standing by to answer your questions on the fly, and we will also be going through all the questions in our Q&A at the end of this session. All right, so we can see right now that we are hitting our target frame rate pretty comfortably. If we full screen, we are not so comfortably sitting at 26 milliseconds per frame. Let's also go ahead and bring up our unit graph and see what's going on here. So we can see right now, if we hit Control Shift comma, that it looks pretty obvious that there is something else going on besides what's happening in the scene. The actual scene thread is eating up 18.8 milliseconds. Our planar reflections on the floor is eating up 6.44 milliseconds, which sums up, basic math is pretty hard. Let's say that brings us somewhere around 25 milliseconds. That still means that we have some milliseconds which are unaccounted for in our final render cost, which you can see in the top right frame is taking at 26 milliseconds. So it's close, but there's still a little bit extra. We're also now going to hit Control-Alt-Delete. We are going to bring in our task manager in order to bring in performance and take a look at our GPU. So here we can see that our GPU is taking at 100%, which obviously makes sense when this is what's bottlenecking us. Let's just go ahead and go out to full screen. Let's also go ahead and look at something else. I'm just going to look into the floor because the less we're rendering, the less overhead on the GPU. As you can see now, our GPU is taking comfortably at about 50% performance. Let's take a look at what happens if we go ahead into the setup routing panel, and we're just going to add a separate media input. The media input is going to be full resolution, full HD at a fairly high frame rate. So we're going to go ahead and add an input media. We are going to go ahead and route that into our input field here as media debug in on spigot 1. And in the background, we see that we are seeing some flickering. Our video signal, our pipeline is updating. And if we look very closely here, we can see now that we've chunked up a little bit more of our GPU performance. Let's go ahead and add another input. It's going to be yet another media debug in on spigot 5. And giving this a second to catch up, see here. Make sure we enable VSWIG as well. Oh, we didn't have VSWIG enabled from the get-go, so it's not going to be a very accurate result. But basically, as we keep adding input streams, we will see that they will linearly increase the cost on the GPU. The reason for this is our render pipeline is highly efficient, but there's still a cost to it. Every time you add an SDI feed, or basically every time you add a media input feed, it's going to add a flat additional cost, which is based on the resolution and frame rate of the media, not on what's actually happening in the scene. This means that it's a predictable, reproducible cost, but it's a cost nonetheless. So we're just going to go ahead and get rid of these media inputs now. It's one down. And the other one, we're going to leave the other one. So we're still now going to have the overhead of the extra media inputs. But notice that if I hit Control Shift comma, we can see that, of course, we have preview on, VSWIG enabled, so I'm rendering the scene twice, which is this chunk here. But no matter where I'm going to look right now, whether I try to break down, for instance, what's happening in the scene capture and look at where the frames are going, I'll see that disproportionate amounts are being used by, for instance, calculating shadows. You can see that disproportionate amounts are being used by shadows here as well. This might not actually be factual. Some of the render overhead of the pixel pipeline might be not quite correctly being listed as performance overhead within the GPU profiler. So the big takeaway here is that one, every time you add a new feed to Pixelop, it's going to add a flat amount of performance impact. And two, we cannot accurately debug this impact from within the real engine. You cannot clearly tell whether or not this overhead comes from Pixelop. So this is why we're flagging it, so it's something you can be aware of. Let's just go ahead and remove this. When we quickly have added and removed several media inputs and output sources, there's odds we might have some routing still lurking in the system here. So I'm just quickly going to go ahead and reboot Pixelop. Just to ensure we've cleared all our STI routing, so we don't have to fiddle and override any spigots. All right, so now that we are back, we're just going to jump into our project. And then we are just quickly going to move on and look a bit on, we're going to take a quick glance at lights, shadows, and reflections. It's also worth mentioning that the input type in terms of performance also matters. If you are using, say, a keyed signal rather than just an input camera signal, that's also going to take a few percent more off of your GPU, which means you have a slightly smaller budget for your graphics happening within Pixelop. There are, of course, workarounds in terms of using media. If you wish to have a lot of virtual monitors, for instance, where you all feed in separate video sources to all of them, you might be interested in trying to use live media feeds through Ethernet or other ways of streaming data rather than forcing everything to go through the Aja card. Let's see. Let's just quickly go ahead and check our routing. This seems good, so we're going to leave it as is. So now that we're moving on, we're going to take a look at lights and best practices when it comes to lights. We are going to start from scratch in a dev folder. It's starting to get pretty cluttered here. I probably should do some spring cleaning, but we're just going to go ahead and make a new folder. We're just going to go ahead and make a new level light showcase. And we're going to go ahead and open this up. Backdrop, do we have to save that? No. Okay. So what we're going to take a look at here is lights, light bakes, and what that actually means. We've talked about it. I believe Jonas has probably showcased it a little bit, but now we're going to learn how we actually do our light bakes and what that can net us in terms of performance and visual fidelity. So we're just going to go ahead and quickly build a little set here. I'm just going to add a little floor. We're just going to have a singular directional light source. I'm going to hit Control-Shift-, just to quickly check if I forgot to turn off ray tracing. No, we do not have ray tracing here. Good. Since we're going to be focusing on working in the Pixelop editor, we don't really care about our live output feed for now. I'm also going to go ahead and go to World Settings and disable Visivik. Very good. And we're just going to go ahead and wrap up our little set here. It doesn't have to be too big. We're going to simply have a floor and 4 walls. Let's not make these too tall. Something like that maybe. Perfect. Let's shuffle this over there. Shuffle this over here. Let's just block this completely in. Excellent. Okay, so now we have built our gorgeous virtual set ready for prime time. We have our directional light source here. You're going to angle it like so, just so we have it coming in at the 45-degree angle. Let me just go ahead and make this viewport a little bit bigger so we can all see what's going on here. Probably don't necessarily need to see the modes tab. There we go. All right. Then we're going to go ahead and set our light to movable. We're also going to need a talent in here. So let's go ahead and add that. Since you're going to be messing with baked lights, why don't we just use a static mesh as a talent? Let's go ahead and let's see. I think we have some nice looking statues we could use. Let's just go ahead and use this one. Let's put it here halfway in shadow. Okay. Now, what do we have here? We have a virtual set which is currently being lit by a singular directional light, which is set to dynamic. A lot of the scenes and sets we've looked at over the past week has been using light scenarios like this, where we have lots of light sources, all dynamic, which allows us to do things like rotate lights on the fly, change light colors, light intensities on the fly, move objects in and out, which then are being lit dynamically, and do all kinds of interesting things. But there are downsides to using all live lights. For instance, our talent is completely black. We can't see it at all, say from this rim, because there's no global illumination. We could, of course, enable ray tracing, which would add a large amount of performance overhead. What we will typically do instead is, as lighting artists, we'll simply fake bounce lights. For instance, here, we could, instead of accepting the fact that the talent is going to be in shadow, we could go ahead and add a point light. We could turn off cast shadows on this point light. We could then set the point light to not be physically correct. We not have an correct inverse square fall off, but instead just have a nice, more uniform one. Give it a bigger range, a softer light source. Do something like this just to get some nice fake global illumination into the corners. Let's take a look at what we actually have here. So now we've lit our character. We have fake bounce light coming from the front. We're going to go ahead and hit Control-1 to save this camera position, which allows us to at any point hit 1 to go back to this camera position, so we can profile and test things from the exact same point of view. So now with this setup like so, we're going to full screen, and we're going to take a look at our performance. Hit Control-Shift-, there's not a lot going on here, so with our current light scenario, with 2 lights, we're currently using up 0.37 milliseconds. This is of course fine here, but if this was a more complex virtual set, if we had a big environment or tons of heavy geometry, the directional light, instead of eating up the 0.25 milliseconds, which is currently doing, it could just as easily have been eating up 2.5 or 5 or 10 milliseconds, which is more typical to see the moment the complexity of the scene starts to go up. When you start adding a few virtual characters, the cost really skyrockets. So now let's just pretend this is not a decimal value and our directional is actually using 25 milliseconds, just for the sake of this practical example. Now let's see what happens if we bake the lights instead. Since we're going to bake lights, we don't need our fake bounce light anymore. We're going to have correct bounce instead. We're going to select our directional light. We're going to go to details and ensure it's set to static instead. You can see now that when we toggle from movable to static, the resolution goes down a little bit of the shadow. We can also see we get this preview text in the shadows telling us that Unreal Engine is expecting us to try to bake our lights. Baking the light means that we are actually going to be doing a ray trace of the entire scene. We are ray tracing everything and baking down the light data to a separate list of textures. Each individual geometry in our scene, even if it's copies of the same geometry, get their unique light bakes, meaning that we get all the benefits of a ray traced light scenario, but with none of the attached cost. It's all going to be stored as image files, which means that the overhead of calculating the light goes away completely because the light calculations have been done ahead of going live. We are going to access light builds, all you have to do is at the top here, hit this drop down. Here you can select build lighting only. Before we do that, we're going to ensure that our lighting quality is set to preview, because we don't really care about full quality as we're just testing and blocking things out. We just want to see a quick, rapid turnaround example of what our bake is going to look like. Then we're just going to go ahead and hit this drop down. We can hit build lighting only. Before we do that, it's usually a good idea to give the engine some information about where your important position is, like where do you want to focus the quality of your light bake. To do that, we can simply add a light mass importance volume. Let's pull this in, and you can see here we have a big, nice looking box. This is simply a volume that you can use to block in your studio to tell the light bake this is the area that we need to focus on in terms of baking quality. This is especially important for light mass irradiance probes, which basically is volumetric light data allowing us to bake light everywhere in the scene. So as we add dynamic objects later on, they will still be able to be lit from our baked light scenario. So you can see here we add light mass importance volume around our studio. And we are just going to now go ahead and hit the drop down and build our lighting. And you can see that it goes lightning fast. If we were to take a look at our swarm, which is what's handling our light bake, let's take a look at the swarm agent here. We can see that within our current studio setup, we actually have distributed light bakes. It's trivial to set up light swarm on your artist machines, allowing you to distribute these light baking operations across multiple Unreal engines. The benefits of doing this is, as you start approaching production quality lighting, when you want to sort of do your final lighting passes and you have very complex, heavy scenes, doing a light bake on a single machine can start taking several hours, which is not really ideal in a typical work scenario. Distributing the workload across multiple render engines will allow you to still have acceptable turnaround times despite trying to bake very, very high quality lights. Okay, so let's see what we have here. So now we've baked our lights. If we hit 1 to snap to our predefined camera position, we can see we have some obvious issues. We'll be addressing these immediately after we take a quick look at our performance. So hit Control-Shift-, and we can see now that the render overhead for light has gone away completely. If we see selected here from the dropdown, we are currently using 0 milliseconds down from 0.37 to calculate our light setup in the scene, which is a huge, huge benefit. Ignoring post-processing, which doesn't tend to fluctuate a lot, we can see that this has drastically improved our overall render performance within this environment. Let's start looking at the issues. First of all, the pros here is that we have pretty good looking bounce lights now. Given that this is a perfectly white surface, we are expecting to have very bright bounce. But we can see that the resolution leaves something to be desired. This is supposed to be a sharp fall off on the wall here, but it's all very pixelated. Same on the floor. Let's hit Alt-6 to go into lighting only mode. You can also do that from the drop down here to go to lighting only, which will allow us to ignore the material on the statue and focus on the light bake. The statue seems to have fared much better. It has good looking crevices. We have some nice looking ambient occlusion. We have some artifacts here where we can see the UV seams exist. But once the materials come back on, this is really not very noticeable at all. If you didn't know these artifacts were there, you wouldn't see them. Okay. We are also just quickly going to go ahead and dive into our post-process handler and ensure we've turned off ambient occlusion. Just so we know that all the ambient occlusion we're seeing in the corners is what's actually being provided by our light bake. So due to the low resolution, we can also see here that we have light bleeding through this very thin wall. And this is a common light bake issue within Unreal. If you have very thin walls, you will often have issues with light coming through. You can either resolve this by having thicker walls, or you will have to increase the resolution of the geometries of the light map. You would have to increase the light map resolution of the geometries where you're seeing these artifacts. Now, we're going to go ahead and select all these cubes, and we're going to go to the Details tab, and we're going to search for light map. You can see here that the default light map resolution, the texture which is currently being baked for these giant cubes, is 64 by 64 pixels for the entire cube. If you do some simple math, you realize that that is not a whole lot of pixels per square foot. We can even see what these bakes look like if you go to world settings and scroll all the way down to light mass. This is where you can set all your render settings for light bakes, like how many bounces are you going to have, what's the density of your volumetric light map going to be. What that means, we're going to look in a second. How much do you want to boost your diffuse versus your environment versus your skylight? Do you want to offset the color for your environment? Right now, our environment is black, but we could just have an ambient faint red value, for instance, if you wanted to be somewhere hot and burning. And down here, we can also see our actual light maps. Let's go ahead and take a look at this one. So here we can see all the light bake data for our different geometries have been packed into sort of big atlases where multiple actors have been combined. What we can see here is a lot of the cube surfaces with their different gradients. We can actually see the individual pixels, so it's a bit blobby. And this big chunk here has to be our statue, simply because it's the only organic looking shape within this atlas. Cool stuff. So what we're going to do now is we're going to go ahead and select all these cubes. We're going to select the floor as well. We're going to override the light map resolution. And instead of 64 pixels, let's just go ahead and do a 1024. You'll be surprised by how low your light maps can be and still give you very acceptable results. And you should try not to go overboard on the light map resolution of every actor. Keep in mind that every actor in your scene will need a unique bake. If you have flowers or foliage, if you have 5,000 trees scattered around in your scene, sure, they'll be sharing the textures for their diffuse, their roughness and metallic and all that. They'll be sharing materials, but they will all be having unique light bakes. So just keep that in mind, that light bakes should be as low resolution as humanly possible. We're just going to go ahead and do a secondary build here. The reason we made the cubes so big is because they aren't being used as walls. They're not being left as what the actor was originally designed to be, a small blocky cube, which is why it makes sense for them to have a higher resolution. And just like that, within seconds, the new bake has completed. And now we can see we have much, much, much better looking results. We can see here we have nice looking ambient occlusion in the corners. We can see that the lights clipping through have gone away completely. We can see that there's some sort of bumpiness here. There's almost like there's some noise to the shadow, and that's to be expected. This is a preview light bake after all. We can assume that a lot of these artifacts will go away with a higher quality bake resolution, or sorry, bake quality setting. More importantly, we now have a more accurate fall shadow over the corner here, which even seems to diffuse correctly as we approach the apex of the shadow. And our statue is looking as lovely as ever. Now this light is all baked, but that doesn't mean that we can't do things like add dynamic lights. It's very important to keep in mind that you can freely combine dynamic and baked lights in your scene with no caveats whatsoever. This means that you could bake down your expensive lights like your directional light source, your point lights, and your area lights, but still have large amounts of point lights or spotlights, for instance, which still could be lighting your scene dynamically. As we can see here, this spotlight is said to be movable, and there's no issues interacting with pre-baked lighting using a movable light source. We can also go ahead and add instead of just adding new light sources, we can also do things like, let's say, let's add a new geometry. Let's actually add a forced dynamic actor. Let's add a skeletal mesh, which is always going to be movable. Let's go ahead and pull in Gideon here. Let's not do the red skin. Let's do something a bit more desaturated so we can focus on the light setup. Let's see, let's pull in this one here. This is yet one of the game characters from Epic's Paragon title, which we are pulling in here. Let's just go ahead and give him an animation asset so he can idle instead of stressing around in a A pose. And let's take a look at him. So we can immediately notice that despite him being pulled into a scene with only directional light, we can still see him being lit from the front because he's currently being lit by irradiance probes. As I pull him closer to the wall, we can see he becomes darker. And as I pull him out into the light, he becomes brighter. At Alt-6, so now we're only looking at the lighting, and we can see he's being lit quite decently from the back and from the front. Put him in the corner, he gets visibly darker. Pull him over here, he gets brighter. And also as expected, if we pull him over the ledge, where he'll no longer be getting bounce. Let's pull him away a little bit. Down here, the front of our Gideon is white. As you pull him up, he'll become darker and darker from the front. The question now is, where is this light coming from? Because this is obviously not the textures that we bake down. Textures are assigned to geometries. They don't hang around the 3D space. Now let's go ahead and hit Show. Let's go down to Visualize. And let's take a look at our volumetric light map. That's an exciting title. Let's take a look at it. Clicking this gives us interesting matcap spheres, as they is what they look like, floating around our scene. If we pull out, we'll immediately notice that there's a much higher density of these spheres within our light mass importance volume. You can see in the rest of our black void, they're spaced very far apart. And this is because, again, we used a light mass importance volume down here, signifying that this is where we want to focus our density of probes and light quality. What these basically are is very localized light sources. Every time a geometry moves towards one of these probes, it will assume more and more of the light setup as it is on that particular probe. You can see here the probes in the shadows are dark. The probes here are being lit from the top right, while these of course are not. And if I were to do something like, for instance, add a sphere here, let's go to geometry and just pull in a sphere. There we go. Let's go ahead and scale this down a bit. As you can see, when this sphere is close to this probe, it assumes that light scenario. And as we pull it over towards the right, it will seamlessly blend to the opposite light scenario. Except it's also being lit red by this dynamic light. Let's just hide this for now. There we go. There we go. So now we can see that this is a blend between two different probes. This means a few things. First of all, it means that if we hit Control-Shift, there's still no light overhead. There's nothing happening here that pertains to light. This is all basically free, which is fantastic news. But this also means that if I scale this up, pull this down, let's instead of scale it, let's just use a cube. If I were to pull in a dynamic cube, notice that the cube does not get the same contact shadow as we get from the baked light. This is an approximation. It's great for quickly moving objects just to get a rough feel of the ambient lighting, but you will not get the same correct contact shadows as you'll be getting with baked lights, which is a bit of a shame, but it is what it is. All right, so that is baked directional lights. But we can do other things with baked lights, which is pretty interesting, besides what we currently looked at. Let's go ahead and take our directional light and just delete it. Some of you that probably have spent some time in Unreal know that we can of course light using point lights, directional lights, spotlights, area lights, and skylights. But if we are going to be baking our lighting, we can also emit light from emissive surfaces. which is really cool. So here we have our statue. We can center it here in the middle of our studio. And now, instead of receiving light, this statue is going to be a light emitter. We're going to go ahead and see here. I believe I had the material already set up. Let me just go ahead and filter by materials. Yeah. So here we have a glowing material for the statue. Let's convert this to a parameter so we can change it around. Let's give this a slightly warmer color as well. That's nice. Something like that. So if we go to lit mode, it's a bit hard to see because we don't have any bloom enabled yet. So let's quickly tab over to our director. Let's bring up our production tab. We are going to go to effects, and we're just going to go ahead and enable some nice convolution-based bloom, just so we can clearly see that our statue is glowing, and we can see just how intensively it's glowing. We're also going to go ahead and add a few geometries to block this light, just so we can kind of see how this actually works. Let's also go ahead and add a ceiling just to box in our studio here. And now we could just go ahead and try to bake this. We are also going to, since we are going to be relying heavily on light mass probes within this environment, we're going to go ahead and go to world settings. We're going to go up to volumetric light map detail, cell size. So currently these probes are spaced 2 meters apart, or 200 units. Let's go ahead and space these 50 centimeters apart instead, or maybe even 25 centimeters if we're feeling lucky. And we're going to go ahead and bake this instead. Something that's also interesting is, which you might have noticed, is even despite me deleting the directional light source, we can still see the directional light lighting the scene. This is again because that light data has been baked down to our environment. So now that we've completed our new bake, we can see that our statue is glowing, but it's not actually lighting our scene. This is because I forgot a crucial step. In the details panel for that particular actor, if you search for light, we have to explicitly state that this emissive light object, this emissive geometry is supposed to be actually be lighting our scene when we're using a static lighting scenario. Static lighting and baked lighting is more or less interchangeable. Let's go ahead and build our lighting one more time. You can see now it's taking a little bit more time for what hopefully should be pretty obvious reasons, in that we wasn't actually baking anything the first time around. And here we go. So this is actually rather interesting because this entire room right now is being lit exclusively by this statue. There's no other light source. This is all coming from a singular emissive object. We can even see that we are lighting the back of these cubes because we have, I believe, 3 or 4 bounces set up right now by default. Let's go and take a look under our bake settings. Yes, we have 3 bounces, which means that the light is able to be emitted from this statue, hit the back wall, and the rays then bounce back to illuminate the back of these cubes. Very nice. We can see that the amount of noise has now been greatly increased. We see artifacts, especially along the intersections. But this is, again, perfectly fine and acceptable because this is a sort of an early prototype. This is a preview and not a final light bake pass. If we hit G, we can also see that the amount of probes we have is much more dense. It's actually, this is starting to look rather artsy. And if I do the same thing as before, I go to my content and I pull in the skeletal mesh. You can see that he is again being lit by what is now an emissive object. This allows us to get far more accurate and convincing lights than if we were to, say, just use fully dynamic lights. And again, this can still be spiced up by using dynamic lights if we, for instance, now want to use this baked statue as just a warm sort of global illuminating main light source, but still be able to pull in rectangular lights or point lights and use those to give us some nice dynamic rim. All right. So now we've looked at different ways we can handle our lights. But the issue here is that in order to bake lights in this fashion, we need light map UVs. Let's open the statue and take a look at what the light map UV is. So given that not all of you might be familiar with what the UV or what UV map is, it is basically a way to, it's a two-dimensional grid, it's a map for each point on a 3D model, saying that this point corresponds to this pixel on a texture. Is basically, think of it as origami. You have your 3D geometry, you cut it up into tiny pieces, and you have to unfold those pieces onto a flat square. So here we have a 3D model, and if you take a look at the UVs, we can here see that the UVs are being cleanly laid out on this square like so. We can even identify certain parts of this geometry. The problem here is that this does not actually have dedicated light map UVs, which is fine, because these were still evenly laid out UVs, so we could use these to do a light map bake. It's very typical within Unreal to have separate UVs for light bakes. The reason for this is, as you can see here, these UV islands are packed very tightly together. There's not much space between some of them. But by default, UV light map bakes or light maps for an individual asset tends to be a pretty low resolution. If we were baking a 64 by 64 light map for this model, you would start seeing excessive bleeding. Like if this island here on the left was purely lit by directional light, so this would be very bright, and this island on the side here would be in shadow, so perfectly dark, you would start seeing bleeding across here where dark pixels from this side would bleed over to this side due to MIP maps, or vice versa, you'll see bright pixel bleeding through here onto the dark section. This means that we have to make separate light map UVs where you have better spaced tiles. Luckily, this can be automated within Unreal. You don't have to do this by hand as we had to do back in the day. Simply search for light map. All you have to do is in the static mesh actor, enable generate light map UVs. The light map UVs is going to go to a separate UV map with index 1. So let's ensure that we are going to be using light map coordinate index 1 for our light map bake. And now the moment we do that, we can see something is being built, and then our Unreal crashes. Terrific. Let's dive back in and let's try that one more time with feeling. Building things within Unreal can do this on the occasional basis. It's something you'll get used to. All right, now we are in the wrong level, so let's quickly dive into the not wrong level. That's probably going to be tucked away underneath our light examples folder. Here we go. Luckily, we had an autosave, so we still have our light scenario in place. Okay, so we're going to go ahead and select the statue, and we're going to try this one more time. So we're going to set the light map resolution to 128. We're going to set the light map coordinate index to 1. And this time, we are just going to, let's see, this is correct, this is great. We're going to generate the light map UVs. The last thing we're going to do is scroll all the way down and hit apply changes to the changes we just made, which basically is we hit this checkbox and ensure that we're going to actually use the light map UVs we're generating. Let's cross our fingers. And now we can see from this dropdown, we have a separate UV channel, and these are our light map UVs. What Unreal does here is it takes the islands we have already generated. It doesn't actually unfold anything, and it simply lays them out and spaces them in a layout which is much better suited for light baking, which is terrific. Something that's also great is if you have a large amount of assets that where none of them have light map UVs, maybe you just imported something from Cinema 4D, like a full set, and you intend to build lighting for this, you can actually change these parameters across multiple actors at the same time. For instance, here, if I just want to change these 2 actors, I can select all of them at the same time. I can right click them. I can go to asset actions and bulk edit via property matrix. And from this window, you can actually apply these same changes to multiple actors at the same time. I've used this to do batch operations on hundreds of static meshes at the same time. It does, depending on what you're doing, you're probably going to crash 50% of the time, but it's still going to save you dozens of hours of work. It's an operation you can restart within 30 seconds, and it will just churn through any amount of actors without a hitch, which is absolutely fantastic. So you can see here underneath LUT settings, you can change any kind of parameter. See here, we can set light map resolution to something overridden on all of these. I can forcefully set all of these to generate light map UVs by clicking this checkbox. I can say that all of these are going to have a light map resolution value of 512, and so on and so forth. Let's just toggle this on and off again to force this to recompute. And now that we're done, we can see all of our geometries have been changed. And if we were to open this other one here and now, we can see that we have our light map UVs. On this one as well, if we were to look at our light map UVs, we can see that this also has light map UVs. Now these UVs are hot garbage. We can see that more or less every single polygon has gotten its own island, which is not really ideal, but it's still going to bake surprisingly decently. The most important thing is basically that geometries have their own place on the UV island. Even if like an entire petal here gets a single pixel of light data, that's preferable to having a front and a back face where the front is bright and the back is dark, having to share the same color data. Let's take a look at what happens if you have a geometry that does not have light map UVs and you try to bake it. Let's just quickly cook something up. Let's hop into a 3D model suit of choice. We are just going to make a Susanna head. There we go. I have a beautiful monkey. We're going to subdivide it. We are going to collapse it. And what we're going to do here is we are actually going to do a UV project from the front. So we're just going to go ahead and project from view. There we go. Which means that this monkey head now has the same UVs from the front and back, as you can see here. This is going to give us some interesting issues when we put this in and try to bake it. I'm going to export this as a geometry. We are going to go ahead and export that to my documents folder. Let's pull that into our scene. Do I have a browser view anywhere? No, I do not. Let's see here. Oh, there we go. Sorry for all the tabbing. Don't mean to be disorienting. We just have to get this done. So here we have our monkey head. I'm going to pull that in. We are not going to generate lightmap UVs, so we're leaving that turned off. We are not going to create any materials. We're just going to go ahead and import Susanna. Terrific. We are going to put the monkey head here, scale it down a bit, and we are going to set the front to be pointed towards our statue or our light source, whereas the back is going to be completely in shadow. Right now that looks pretty good because it's being lit by the light mass irradiance probes. It's not being lit by a light bake. So you can see this doesn't actually look half bad. It's being lit pretty decently. Now we're going to go ahead and hit build lighting only. Let's also feeling a bit bold, so let's go ahead and bump that quality up to high and do a light mass build now. Oh, there we go. It's also worth keeping in mind that baked objects cannot be moved during runtime. If you bake lights onto your virtual set, you obviously should be trying to only bake lights onto things that are not meant to be shuffled around. If you have, say, a virtual monitor or a video wall that's supposed to be animating in or rotating and pivoting and all kinds of things, that geometry is going to have to be dynamic, which means it's either going to be lit using irradiance probes or it is going to have to be lit using dynamic lights. But as for lights themselves, the more spying eyes among those of you in the audience might have noticed that there's more than just a static and a movable setting for a light source. There's more than just static for baking and movable for dynamic. There's also stationary. A stationary light will have its shadows and bounce lighting from static geometries baked into light mass, also into the light map textures. But a stationary light will still be able to light dynamic objects as if they are dynamic. These light sources cannot move, but they can light both dynamic and stationary geometries just fine. So in edge cases, if you're in doubt, if you plan to bake lights, but you still need the light source to interact with moving objects, you still have the option of using stationary light sources. All right. Now we can see our bake is complete. It was lightning fast as it was distributed. So here we see we are getting a warning. Susanna has overlapping UVs. We can even see that exactly how overlapping they are. The UVs are overlapping by 54.9%, which is a lot. Please adjust the content. And here we can see how this is looking now on poor Susanna. So she has a 64 by 64 resolution light map, and we can see we have big issues with artifacts. Hitting Alt-6 for lighting only shows us that some pixels, like these here, are being lit correctly, but suddenly we have a smear of shadow over her right eyeball. This is because the back and the front shares the same pixels. So it's completely arbitrary, it's completely random whether a pixel is being lit as if it's in shadow or if it's in light source. You can see the same thing on the back. All of this is supposed to be in shadow, but suddenly we have areas which are baked as if they are being lit. This is why it's important to have light map UVs. Another issue with Susanna is that her UVs are actually completely atrocious right now. Since we did this projection, there's not actually separate islands. This is not the same UV flipped, mirrored, and overlapped. It's actually a single continuous tile. The issue here is that now if we try to say, you know what, I want to quickly generate some light map UVs. So I search for light map, I set the resolution to 128. I want to use these in coordinate 1. I'm going to go ahead and generate light map UVs. We're also going to go ahead and hit apply to these changes. Where is light map? Light map. There we go. Light map coordinate in this should be 1. If you look at the, oh, this is, I wasn't expecting that, I have to be quite honest. So what we see here is that Unreal has actually managed to cut up our geometry, our UVs, and done sort of an auto generation of light map UVs. I was actually expecting this to just look the same as the UV above. So I am very pleasantly surprised. I haven't tested this in a while. But this is fantastic because this means that now if we were to do a secondary build, it would work as intended. We can also see here that since we are now baking with a higher quality setting, a lot of the artifacts we saw along the wall and in the corners have now been rectified. They are completely gone. But since that takes a longer time, we're just going to crank this back down to preview, and we can do one last quick build and see how this looks with the final UVs for Susanna. And this is more or less the pros and cons of using dynamic lights versus baked lights. To summarize, dynamic lights give you unlimited freedom. You can change them on the fly and do a lot more interesting animations and such with them. But with baked lights, you no longer have to worry about the amount of lights you have and the quality of the lights you have. Yeah. So you can see the light map UVs are not perfect. There's still some overlap, like here behind the eyebrows, which I believe I actually saw here in the UVs as well. Yes, so here at the front of the monkey head, we can see there's some overlap where the eyebrows overlap the head itself. So this is still not a perfect solution, as we see some artifacts, but it's still a lot better than what we had minutes ago. All right. So the next thing we are going to take a look at, now that we have looked at light bakes and how to get the most out of them, let's take a look at reflections. We are going to be looking at screen space reflections, planar reflections. We're also going to look at reflection captures of different kinds. And I think we're going to leave it at that. We are not going to spend a lot of time with ray trace reflections until later today. So, reflections. Let's go ahead and move this sweetheart over to the corner and reintroduce a directional light source. There we go. Just so we have something more interesting to work with. We are also going to take the floor of our virtual set here and give it 2 different levels to allow us to highlight some of the pros and cons of using screen space versus planar reflections. All right, it's starting to look rather beautiful in here. This is more or less a esports production ready to go on air. So the first thing we're going to take a look at is screen space reflections. These are the cheapest reflections you can use. They are not very physically accurate, but they give good results at a completely insignificant performance cost. They are great to use, especially when you have very bumpy or organic environments where you just want some kind of interaction between your different scene elements. In order to accurately be testing this, we're going to go ahead and just slap together a quick material for our floor here. So let's just go ahead and make a new material. Shiny floor. Very good. This is new material. We're just going to quickly make it, give it a metallic value of 1. We're going to give it a pure white color of 1. We're going to give it a roughness value of 0 to make it perfectly reflective. And we're going to go ahead and just grab a detail normal map from somewhere in our project. There we go, just to give us some breakup so it's not a perfectly reflective surface. Let's go ahead and hold the U key while we click to get the texture coordinate node. Let's hold M for multiply and just multiply this by 50. This is going to allow us to tile our UVs, as you can see here. This is currently our UV coordinate for this plane from 0 to 1 along X, which is red, and Y, which is green. But when we multiply it, let's see, we can actually visualize that, can we? That's not going to be. What is that node again? Give me a second. Again, the Unreal Engine documentation is a fantastic source for knowledge and looking things up whenever you've forgotten what you try to find. So I was actually looking for, where is it? Fmod, that's the one, which basically only gives me the decimal and not the whole numbers. So I am going to go ahead and do an Fmod, I believe, based on a value of 1. There we go. Perfect. So you don't have to understand everything that's happening here. All you have to understand is the fact that now we can see this is a single UV space, so basically a single tiling of a texture. And here, as we multiply it by 50 and Fmod it, we can see that we are basically tiling our texture 50 times along the span of the same surface. We could even make this a scalar value, so we can just call this tiling. So here we can see we tile it once, 2, we tile it twice, 3, we tile it 3 times, 8, we tile it 8 times, and so on and so forth. So 50, we plug that into the UVs for a normal map, which you can see now is it's tiling a normal map 50 times, just to give us some small level grunge. The last thing we're going to do is take this normal map and just flatten it, promote this to a variable, and we're going to set the flatness to 0.8, which means that we are reducing the normal map intensity by 80%. Then we're going to plug that into the normal of our material. We are going to stop previewing this and look at the final output. And now we have a nice chrome ball, which has seen better days. It's gotten banged up ever so slightly, which is perfectly fine for our needs. Now we're going to go ahead and take this chrome ball material we just made. I'm going to go ahead and drag it onto my floor surfaces. And now we're off to the races. So, first observation, this floor is not very reflective. It seems to be reflecting something here, which I believe is our directional light source, this is a specular reflection, but it's not actually doing a very good job of reflecting anything else. It's all rather black. The reason for that is we haven't actually introduced a single type of reflection into our scene. Before we start doing that, we need to understand how the reflections work in terms of interacting with each other. There is a hierarchy or sort of prioritization order in terms of reflections. What this means is that for any particular surface or geometry or 3D position, if there are multiple overlapping sources of reflection, like if you in the same space have both a reflection capture actor as well as screen space reflections, as well as planar reflections, then the most complex, good-looking reflection type is going to take priority. If you have screen space and planar reflections in the same area, we are only going to be seeing planar reflections in that region. So for now, Keeping that in mind, we're just going to go ahead and go to our post-process volume or post-process handler, search for screen space, and enable the intensity and set the quality to 100%. Lowering it basically just lowers both the resolution as well as what is being reflected. Then bringing it up gives us nicer looking reflections. And just on that note, we can now immediately see that we are reflecting things onto our floor, which is great, but we can also immediately see we have some pretty glaring issues. Let's also go ahead and make the upper level a bit more coarse. So I'm just going to go ahead and make a material instance of this shiny floor. Mi shiny floor polished. We're going to open this and set the flatness from 0.8 to 1, which is going to make it a perfectly reflective mirror surface. And we'll apply this to the upper level. This is only so we can see the actual full resolution reflections. And as you can see, this looks pretty good. We can see that we are reflecting our actor. The spacing seems to be good, despite this type of reflection not being based on 3D space or anything at all. This is a reflection which is completely based on different buffers in the Unreal composition pipeline, and it's very much sort of a hacky approximation of what the reflection is actually supposed to be. Something that is the first and biggest obvious issue with screen space reflections is that it can only reflect what is currently on screen. What we can see here is that in the bottom right and bottom left corner, we see some black artifacts where it's currently trying to reflect things outside of the range of the buffer we are working with. As we tilt our camera down, we can also see that the more of this wall disappears up out of our frame, the more we eat away our reflections. And when we are not looking at the wall at all, the reflection of the wall goes away completely as well. Same with these pillars. As we tilt down and start eroding these pillars, the reflection also goes away. Now, this doesn't have to be the end of the world. Screen space reflections is meant to be this rough approximation. And if these geometries were a lot less planar, than this perfect mirror surface of the floor is, let's say the reflective object was this head instead. It might be a bit hard to make out here. Probably needs some environment details. I guess that's not the best use case, but basically, screen space reflections are great for these kind of complex geometric shapes. But we are now going to take a look at the next kind of reflection, which is planar reflections. Unlike screen space reflections, planar reflections are prohibitively expensive. What the planar reflection does is it acts as a mirror surface. You can see here that the planar reflection actor is an actual large plane. We can see here the bounding box of it is huge. And interestingly, the cost of a planar reflection is not really dictated by the size. Whether your planar reflection is incredibly tiny or incredibly big does not really matter. The cost is the same because the operation is the same. The planar reflection actor basically takes your entire scene, copies it, flips it over the plane. So if your geometry is standing like this, it will now be flipped like this. And we are going to be rendering that entire scene, all that geometry, all over again. So a single planar reflection actor means that we are going to be rendering the majority of our visible geometry twice. But this is also why the planar reflection actor gives us far, far more accurate reflections. There we go. You can see now that we pulled in a planar reflection actor, we no longer have the issue with screen space where tilting down erodes our geometries. We can see that the overall quality seems to be higher. There's less noise. The temporal AA artifact we saw previously has completely gone away as we move our camera. And things just seem to be sticking a lot better. You can see that the moment Susanna touches ground, there's a few pixels here where we're seeing light bleed through Susanna, but besides that, things seems to be sticking pretty bang on. We can also select a planar reflection actor. We can go to the details of the planar reflection actor, and we can start fine-tuning the values for reflection. For instance, we can set the screen space from 50% to 100. Right now, it's impossible to really see what this does, but if we were to pull out here to this perfect mirror surface instead, let's also go ahead and pull the field of view to zoom in a little bit. We can see that the default 50 actually means that the reflection is half resolution. We can see a lot of jagged edges, which is not very nice if you are intending to have a perfectly mirror surface, for instance, a completely flat, non-ripply body of water, in which case 100% is going to look a lot better. Okay. We can also do all kinds of interesting things. We can choose to which extent we want our reflection to be deformed by normal maps by adjusting the normal distortion strength. We can also do some pre-filtering to our reflections to just make them more accurate, I suppose. Let's see, what does this do again? So this is a nice way to hide the fact that you have a low screen space if for some reason you're locked to using that. So it's basically a pulse process effect for your planar reflection. So there's a lot of interesting things you can tweak. You can also choose to selectively reflect only particular actors. Now, we talked about performance. The planar reflection actor is a lot more expensive, and if we were to hit 1 to jump back to our previously predefined position, let's just go ahead and set the field of view back to 90. Now that we're here, if we hit Control-Shift, comma, we can see that our planar reflection actor is eating up a hefty 0.62 milliseconds. Again, this is a very simple scene. This cost could easily skyrocket into both 10 and 20 milliseconds if your scene is a lot more complex. We can then break down this dropdown by just hitting this arrow with our planar reflection actor selected, and we can now see exactly where this performance is being eaten up. So here we can see that we see all the same chunks that make up the default scene render path. We're drawing our objects, we're doing our lens distortion, we are calculating our shadows and doing our lights. We are doing our actual light calculations here as well, drawing our objects, doing all our filtering. Basically, everything that happens in their scene is also happening in the copy of the scene, which is what the planar reflection actor is rendering. This is why we will often choose to use a planar reflection actor only for selective pieces of geometry. We could, for instance, take a planar reflection actor here, and we could tell it to only reflect this particular talent, so we only have accurate reflections from our hero talent, whereas everything else is going to be left as, for instance, screen space reflections. So here we have our talent. There we have our planar reflection. We are now going to go ahead and move down in planar reflection, hit this little drop down underneath, go down to scene capture, where we can choose to, instead of rendering everything, we're going to use a show only list, which now hides everything. We're now looking at screen space reflections, as we can see. And then we're going to use the show only list to only select our talent, which means that we are now only getting screen space reflections of our talent, only getting planar reflections of our talent, whereas everything else is using the much, much cheaper screen space logic. Hit Control-Shift, comma. And as we can see, the planar reflection actor is now a lot cheaper than it used to be. We can actually see exactly what's happening in there by expanding it. Yeah. Yeah. So there's not really anything going on in there right now. But you could, if we have issues where, for instance, we want to reflect a large amount of actors, like here, let's set this back to be reflecting everything. And as you can see now, the render cost for our lights, for instance, is not that high. It's currently at 0.07, but this could easily be a much higher value if we weren't using baked lightings and all that good stuff. Now we actually set our directional to be movable again. So now that our directional is movable, we can see the cost for our reflection has skyrocketed up to 3.64. And by selecting our lights, we can see that, well, the lights aren't that intensive, but I guess none of these are that expensive after actually. Okay, so we're using about 0.14 milliseconds, 0.14 for both our shadows and our lights. What we then could go ahead and do is, if for instance we're using too much time calculating shadows in our reflections, which is very typical, we could just move on down to the show flags of underneath scene capture, where we can selectively choose what we wish to reflect. I can turn off, for instance, static meshes if I only want to reflect skeletal meshes, or I could more likely turn off dynamic shadows. As you can see in the reflection, that does tend to, it kills all the shadows on our talent, brightening them up a little bit, which on a perfectly mirror-like surface is going to be an issue. But if the floor is rougher, like this ripply floor over here, then the issue becomes a lot less prevalent. And now if we were to dig into a planar reflection actor again, we're going to see that the shadow depth cost has gone completely away, and the light cost has also dipped by 0.02 milliseconds. Okay. There's another issue here, however, which is apparent when we put one of our actors on the lower floor and one on the higher floor. We're also going to take our planar reflection actor here, and we're going to line it up. As you can see, we are lining it up with the base floor, which means that the reflections down here look bang on, but up here we are seeing an issue. If we hit Alt-6, we can clearly see that our talent is standing on the floor. He should have contact reflections. But going back into lit mode, we can see that there's a big obvious disconnect. The reason for this is the planar reflection actor is not actually related or tied to any particular geometry. It simply acts as an axis plane, and this is the plane that we are going to be mirroring across. This means that if we wish to have reflections across this floor up here, the planar reflection actor needs to be level with that upper floor. Vice versa, if you want to have correct reflections on the lower floor, the planar reflection actor needs to be lining up with the lower floor. Of course, what we could do is simply use two planar reflection actors. We could take the planar reflection actor, we could go ahead and move over to the distance from plane fade out start and end values. We can actually go into the side view and measure the height of this podium using the middle mouse button. So to go to side view, just click here in the top left and select which orthographic view you want to have. And then I'm going to measure the distance from the base floor to the top of the podium. And then we can see it's currently 35 centimeters. So I'm now going to set my fade out start and end to be within that range. So I'm setting my start to from 10 centimeters to 20 centimeters. And when we've done that, we can see the reflections on the upper floor have gone away, which is because they are now outside the fade in, fade out range for this planar actor. Then we can just copy the plane and put another one on the upper level. And just like that, we're now getting crisp, perfect reflections from both our talents at the different heights along the z-axis. The only issue here is that now we actually have two planar reflection actors. Earlier we talked about the fact that with a single planar reflection actor, we are basically rendering our scene 2 times because it's being mirrored across the planar reflection actor as a axis. If we have 2 planar reflection actors visible at the same time, that means that one of those mirror surfaces will also have to reflect what the other mirror surface is drawing, because there is a chance that these plane reflection actors might be angled at each other, and you might want to see the reflection of one plane in the other plane. In very short, simple terms, this means that if we have 2 planar reflection actors, we are going to be drawing our geometry 4 times. If we have 3 planar reflection actors, we are going to be drawing our geometry 8 times. As you can see, this can very quickly spiral out of control. If we hit Control-Shift, comma, we can already see that one of our planar reflection actors is already starting to chunk up a bit. If I were to take these 2 planar reflection actors, just copy them, angle them a bit, so now we have 4, then we can do the same test. We can now see that the cost for these are starting to spiral out of control. This, at a glance, seems to not be as blatantly painful as I'm experienced with being, so there are odds that Epic might have made drastic improvements on this particular subject. But nevertheless, I would be mindful of using multiple planar reflection actors if you can avoid it. Okay, now let's take a look at fallbacks. As we can clearly see right now, we have planar reflection actor on the lower floor. Let's just go ahead and move that to the upper floor. There we go. So now we have a planar reflection actor on the upper floor. It doesn't extend to the lower floor, which means that on the lower floor, we are going to be falling back to the much cheaper screen space reflections. But we can see that when we are missing screen space data, the reflection becomes black. So we're going to add one last layer of fallback, which is going to be a pre-rendered reflection capture, which you can grab from the Visual Effects tab. There's 2 options here, sphere reflection captures and box reflection captures. Simply put, for square areas like rooms, square environments and such, corridors, hallways, yada yada, you're definitely going to be wanting to use the box reflection capture. Whereas if your environment is a lot more fluid, organic, and doesn't really have as many clear lines and shapes, feel free to go with the sphere reflection capture instead. I am going to use the box reflection capture, which basically is a 360 capture camera. I'm going to put it roughly at where I expect my camera is going to be. I'm going to put it in the center of my room. And I'm going to go ahead and hit Build Reflection Captures. What this does is it actually does a 360 capture from this point of view. And we can see that we're now getting we now are having reflections even if there's nothing for our screen space reflections to work with. You can see here, even if we look completely down, I'm still seeing some reflections introduced in our scene. Let me just go ahead and add a upper level as well. Actually, no, let's not, instead of doing that, let's just add I know what we'll do. Let's go ahead and build our reflection captures to get rid of what we just calculated. And we're going to add an atmospheric fog to give us a nice looking environment around everything else. You can see that this atmospheric fog is showing up as black here. But now when we finally add our box reflection capture, we will center it here in our environment. And we will go to build reflection captures. Now you can see that all those black pixels are being filled in by our box reflection capture. You can see here that where we're currently getting screen space reflections, when we tilt down, the fallback is going to be the capture from the box. And we now have reflections basically no matter what we are doing. This could, of course, be refined further. There's many things we can do to get this to behave in a more sensible way. We could, for instance, take the box reflection capture and actually use multiple ones of them. We could put one in each corner, for instance, just to give us more granular reflections in those regions. Now, as we transition from this corner over to the other corner, we are basically going to be blending between box reflection captures, giving us more accurate reflections in the different regions. And this, of course, looks a bit bogus because the floor is perfectly reflective and there's a lot of artifacting when this thing goes in and out of our scene. But the moment we start roughing up our floor a little bit, we can see that we are getting what looks to be pretty acceptable results. All right, so now we've looked at how we can use light, shadows, and reflections in a mechanically sound way to give us just the amount of quality we expect for any particular region in our scene, and also depending on what we intend to do with the scene. Dynamic environments, we can use dynamic reflections and dynamic shadows on the fly, but we also have the option to fall back to baked lighting and pre-rendered reflection captures. Next up is ray tracing. We've spent a lot of time looking at ray tracing during the last week, but we haven't really gone into depth in how do we get ray tracing up and running in our actual day-to-day environments? How can we actually use ray tracing in a production? And in order to do so, how do we optimize to get the performance we need with ray tracing enabled? We're going to look at how things look with ray tracing as is, which is costly. We are going to then start improving performance by selectively enabling and disabling features. And we're going to look at how this is represented in our actual render times. Before we do that, I am quickly just going to disable a blueprint I have called RTX Toggle, which is an utility blueprint I made to automatically optimize my ray tracing in the set we're going to jump to in a second here. I'm just going to unhook event begin play, which means that everything is going to be default values when we launch the level in live mode. We're just going to go ahead and jump out of this level. The reason we have to exit the level is so we can go to Director, go to Setup, go to General, and enable DirectX 12, which is going to facilitate ray tracing. Then we're going to jump to Launch, Pixelpalooza, and we are going to enter a level Studio. Let's do that in Editor so we can move around and flip things and play around on the fly. Terrific. Now I do have some adjustments here. I don't really know what those are. So I am quickly going to just kill those. Oh, my bad. That might actually be in keyer settings or something. Yeah, that doesn't really look good. Let's go ahead and fix that. As we keep looking at this, just as a reminder, I know there's been a lot of technical information to absorb so far, so please do not hesitate to ask questions, even if they are about very specific things in what we've been looking at up to this point. Or even if they're questions completely unrelated to what we've been covering up until now. Okay, so I'm going to quickly just line up my talent here with the floor, and I'm going to just quickly reset my key from the production tab in Director, Video Keyer. I am going to hit Initialize Key. Can we get our SD output feed visible so the people can see my keying process? With music enabled, now if you look at the side webcam feed, we can see our live SD output feed. I am just going to send my SDI feed to that output signal. We can't see that because I actually have VSwig enabled, so I'm going to go ahead and enable that. I'm actually just going to jump into live mode. There we go. So now we can see the current key. I'm just going to go ahead and reset everything. Hit initialize key, select the background. Just going to select some of my, oh, that was too much. Let's try one more time. There we go. Initialize. That's pretty good. Let's get some of that grunge in here as well. Maybe some of that back. That's pretty good. And then I'm just going to tighten up my key ever so slightly. And there we go. That'll do for now. Let's be a bit gentle with that. Perfect. There we go. That's something I can work with. You can also see that the camera is a bit dark. We probably should have shaded a set of white balance on the camera, but I'm pretty comfortable in my chair. So I'm just going to go ahead and go to color grading, video, enable color grading, and simply shift up our talent just so our talent looks more in line with the environment the talent exists within. There we go. It's pretty aggressive gamma and contrast, but it looks fine, so we'll leave it as is. All right. When I hit escape, I might have to reapply the send STI to, there we go, perfect. And we're just going to go ahead and bake down these settings into our level. There we go. We can change this feedback now. So, ray tracing. So we can see right now that in the set, we are not ray tracing. So bypass, we got some planar reflections. Why do we have that in here? We don't want planar, we want to ray trace. Let's get rid of this planar. Let's take a quick look at our project settings as well. Let's just search for array. And as you can see, ray tracing is disabled because I rolled back the project to a clean, fresh state just before this wonderful session with all my friends over here in the Pixelpalooza Hangout, which means that I'm going to have to re-enable ray tracing in this scene. So I enable ray tracing. I'm going to have to restart the project, and we're just going to bring it back up. And let's go ahead and give this a second. It might actually be up, and there we go. Now this looks more like what I was expecting. I might need to shut this down cleanly, so I'm just gonna reset my settings here. There we go. We're going to go ahead and ensure that VisiVig is turned off because we are going to want every frame we can get right now. The performance here is also going to be a bit extra bad because we've actually intentionally degraded the behavior of this set for the optimization showcase we're going to have later today, but it should still be workable. So on that note, let's just full screen this and let's take a look at what is happening in here. We're still compiling shaders, but we are nevertheless going to go to optimization. We are going to bring in, let's see, our FPS counter. And I think I actually want to be looking at FPS counter as well as stat unit graph at the same time. So I'm just going to type the console command, because if you click these buttons, they will hide everything that you don't currently have selected. So if you want to look at multiple graphs at the same time, you will have to use the console. I'm also going to go ahead and enable some convolution-based bloom just because I find it aesthetically pleasing to look at. Maybe not convolution-based actually. It's going to be pretty aggressive on the performance here. Okay, so now we are going to zoom out and look at our full environment here. And we can see that we are running at a not so comfortable 84 milliseconds per frame or 11.8 frames per second. So we are some way out of our target frame rate count. Let's hit Control-Shift-, to bring up the GPU visualizer and see what's going on. So as is expected with ray tracing, if you don't fine-tune anything, you're going to see that 60, 70, 80% of your overall performance is being eroded away by ray tracing features. These are the base pass, which is surprisingly heavy. Then we have our, so this is not actually ray tracing, this is just geometry and other things. We have our actual light sources, which is probably to a certain extent. I was about to say this is ray traced lights, but I'll be a bit surprised because this should be mainly baked lights. But I do believe we have a few dynamic lights over on the sides, which is probably what this impact is. And the last major chunk is ray tracing for reflections. So the first thing we're going to go ahead and do is disable ray tracing for lights, simply because we already, if we hit Alt 6, we have a gorgeous baked light scenario for the scene, as you can see. So there's no reason for us to do a live ray tracing of our lights. Why do it in real time when we have gone through the trouble of making lightmap UVs and done a ray traced light map bake before runtime? It simply does not make sense. So I'm going to go ahead and hit insert to bring up my console. And we're going to start typing console commands. All ray tracing settings are going to be pretty console heavy, but don't be disheartened because they're very easy to navigate. Pretty much every render setting within Unreal, if you want to turn anything on and off, you're going to prefix it with an R for render or rendering. Dot. In this particular case, we're going to look for ray tracing. So let's just type ray. And as you can see, here we have access to all the ray tracing settings on the fly. Now we want to start by doing something to our shadows or lighting our shadows. So I'm just going to search for shadows. There we see shadows. I'm going to set our shadows to 0. And immediately we can see in the graph in the lower left corner that our performance improves. We've gone from 84, 85 milliseconds to 56 milliseconds. Let's actually go ahead and just lock a nice frame here just so we have a reproducible scenario to come back to. I'm hitting Control-1 to save this position. So now we can at any point in time snap back to this position. All right. The next thing is ray tracing reflections. In terms of reflections, there's a lot of things we can do here. We talked about plane reflections, screen space, as well as reflection captures. Right now, all the reflections we are seeing are ray traced. Even on this very rough floor, we are seeing ray traced reflections for these light fixtures, for these illuminated beams. On the metal fixtures, we are seeing ray tracing off of both the light fixtures in the ceiling and the orange carpet. But generally speaking, we don't really need to be using ray tracing for very rough surfaces. It is actually not ideal. It might be hard to make out on the feed. I'm going to stop moving the camera. But if you look carefully, you'll see there's a lot of crawling noise on this rough surface, which is a typical ray tracing artifact when you have very rough surfaces trying to apply ray tracing. The reason for this is rough surfaces look rough because they diffuse light, they bounce off the light that hits the surface in different directions, which means that in order for rough surfaces to have good looking reflections, they need to have lots of bounces, lots of samples. But right now we are doing a single sample per pixel, as opposed to, say, a Pixar animated movie where you'll be doing 10,000 samples per pixel. Luckily, there are some things we can do to improve that. We are going to do something to our reflections. So r.raytracing.reflections. And here we see we have a lot of options. Now, we might not know off the top of our head what all of these do. Luckily, there's, of course, the official documentation, but there's also some help utility directly within the console. For now, let's take a look at screen percentage. This seems useful. Let's find out what this does by just select it and add a question mark at the end. Now we can't actually see anything because we have to go to the output log, where we can see a description of what this particular functionality does. r.raytracing.reflections.screen percentage. Screen percentage is the reflection should be ray traced at. By default, it's full resolution or 100%. So now if I were to set this to, say, 50, We are now basically doing half resolution ray tracing. And this should have a very significant impact in my overall performance. As you can see over in the graph on the left-hand side, we are going now from 70 milliseconds to 45 milliseconds, which is a pretty significant bump. We're still not quite at the 50 FPS we need, but it's a good start. Next up is we still have the crawling issue on the rough floor. As a matter of fact, it looks even worse. But we don't have to use ray trace reflections for everything. We can use the other methods in conjunction with ray tracing. We could, for instance, reserve ray tracing for just our most shiny reflective surfaces, like the metal bars on the sides, the chrome circle up on the podium, the glass surfaces, and the metal bar scattered on a set. And then we could just use screen space and reflection captures for all our more rough surfaces where all the extra detail from ray tracing is wasted anyways. In order to do that, we are going to set a max roughness value. This is going to add a cutoff point where we say that every pixel above a certain value in roughness is not going to be ray traced. I'm going to go ahead and set that cutoff at 0.3 in roughness. Just like that, the floor is no longer ray tracing. It's not a significant jump. We actually improved from 45 to 40 milliseconds. We could also make this a bit more aggressive, set it to 0.2, which gives us yet another 5 milliseconds from 45 to 35. We are still getting some of that nice orange reflection here in these metal bars. The chrome up on the stage here is still ray tracing fully because it's a perfectly reflective surface. Same with the glass over on the side. But the floor is no longer reflecting the same way it used to. We could then go ahead and go to our post-process volume, search for, let's say, screen space, and use that in conjunction. Let's see here. Not sure I'm not seeing anything there. It might actually be overridden by a box reflection capture. But that's fine. We can go ahead and use a box reflection capture instead as well. I could here maybe add a more localized box reflection capture closer to the floor level. We could hit build. Let's pull this further out so it's bound to pick up some of that nice orange. Let's hit build reflection captures. It's still not quite what I was hoping to see. So let's go ahead and add an even more localized one to these orange fixtures. Doesn't really need to be this massive element. Okay, so this is not behaving as intended, so I'm not going to spend too much time figuring out why they're not kicking in. We can simply fall back to a planar reflection actor instead. Interesting. Something is going on the set. Let's go ahead and kill these actors completely. Let's do a build reflection captures. And let's go ahead and pull in a visual effect sphere reflection capture. And do this from scratch. Build reflection captures. Nice. So this is pretty big. This is going to be a main reflection capture to cover our entire scene. And then we can go ahead and add a more localized one here for these smaller regional areas. One over here, and one over here. Just like that. There we go. It's not going to be perfect, but now we can see we still have that sort of nice orange sheen on the floor, which is not based on ray tracing. So it doesn't really have the overhead cost of ray trace reflections. And over here, we are now still getting that nice. So over here, we are still getting that correct ray trace reflection off of the carpet on the floor. It might actually be a bit too low. I'm going to set this back to 0.3 because I can see these metal bars are a bit rough. So there we go. That's more bang on. So now we've fine-tuned our reflections. We've fine-tuned our shadow catcher. We can see the crawling on the floor is more or less gone. There we go. Now it's more or less gone. And the last thing we're going to take a look at is glass. So here, this table over here is not ray tracing correctly at all. We can see this is refracting, but this is using the native and real refractive model for glass, which is not physically accurate. You can see we have some obvious artifacts at the edges of the table. And this is because I believe ray tracing for translucency is not enabled by default. So let's go ahead and do that. Ray tracing.translucency, let's set that to 1. And that we can see some obvious issues right off the bat. But before we do anything, let's also ensure that the refraction is enabled as well. So something that's a typical issue with glass and ray tracing is that a lot of glass shaders in Unreal are not built in a physically sound way. A lot of common ways of generating glass in Unreal is using hacky workarounds to make surfaces that look like glass when you are working within the limited non-ray traced standard render pipeline of Unreal. You have all kinds of surfaces that have all kinds of crazy Fresnel-based colors. You do have semi-metallic surfaces to get semi-metallic behavior to pick up some color from the reflection. You have all kinds of multi-layered geometries for car glass to simulate how light bounces off a windshield. But the moment you start actually trying to simulate this using ray tracing, it all falls apart because it has not been built in a physically sound way from the ground up. Luckily, we have another glass shader at the ready for this table. Let's just go ahead and search for glass. I believe it's going to be this one. Oh, that is not the surface I wanted to put that on. Let's try to go ahead and put that on the actual glass tabletop. Is it this one or that one? It might actually be this one. Let's just go ahead and give it a second. If you don't see anything in a few seconds, I'll try this one instead. Yeah, I think that's actually going to be the one. So here we have a glass shader that looks a lot more correct. We're kind of missing some reflections here, so let's go ahead and also pull in this local sphere reflection capture for this talent position, these desks and such. Let's go ahead and make it a fairly small reflection capture. Let's keep it regional for this side of the podium. And let's just go ahead and do a quick rebuild. There we go. Oh, that's a shame. Crashes are not unheard of when you're working with ray tracing, but let's just quickly dive straight back in. My mistake there was working in full screen in what was currently a very poorly performing corner of our environment. When you have screen-based, when you have render effects, which is based on how many pixels you're drawing, for instance, ray tracing, I mean, the more pixels, the more you have to ray trace, it might be beneficial to work with a smaller viewport visible, simply because it will give you a more smooth frame rate experience. I'm just quickly going to keep in the up arrow just to re-input everything we've been using so far, because I haven't actually saved these to the level yet. There we go. So now we're back where we left off. And now we can dive back to where we were working. So here we have our glass table. We're going to select it again, go to content browser, search for glass, and reapply the glass material we had singled out. And there we are back on our feet. So we can see right now that this glass shader looks rather appetizing. It's correctly giving us the nice bounce off of these hot spotlights up above. It's from below, we can see it's actually not looking the way it's supposed to be. So it's not as appetizing as I was expecting, truth be told. What is going on here? Just give me a fraction of a second just to ensure I'm using the correct material here. I am not, thank you. It was simply not on compiling. There we go. I was a bit surprised by what I was looking at. It was not really the visual fidelity I was expecting. There we go. So now we finally have a correctly behaving glass shader. We can see it's refracting correctly. You can see we have this sort of lovely warping of the metal. So it's giving us a lens-like glass refraction of what's happening underneath the desk. We can see those nice highlights of these spotlights up above. And we can see it's actually picking up the heat of the carpet underneath it and scattering it within the glass itself. So this is quite pleasant to look at. Let's compare this with and without ray tracing before we move on. So this is ray tracing off, which is still nice, but it's very gamey. And this is with ray tracing turned back on. Now, as we pull in close here and review our performance, we can see that we are currently using about 70% of our total frame calculation time just on this particular table, which is a bit poor management of resources. What we can do to improve that is several things. First of all, we can turn off refraction, which is notoriously expensive. Turning it off will, of course, get rid of a lot of that lovely interaction with the underlying geometry, as we saw, but it might be acceptable due to the performance boost it gives us, which is not actually as significant as I was expecting. 34 milliseconds. 1 millisecond. That is no reason to get rid of that then. So let's leave refraction on. Next up, we can also see that we can choose what we want translucent to be affected by. We can choose to turn off direct lighting, for instance, which means that we are no longer calculating lights through transparent objects. Sorry, on transparent objects. So we turn that off, kill some of the nice highlight on the side. But the improvement in performance might overall in all be worth it. We can also see that let's see if we can go very close. We have quite a lot of noisy black pixels in here. This is caused by the translucency bias settings. Translucency primary ray bias. This value basically dictates how ray tracing for transparent objects works when close to opaque objects. It's by default a very low value, which allows things to sort correctly. Increasing it might cause sorting to not behave as intended, but it will typically also improve a lot of shading artifacts with transparent glass. If you turn refraction off, we can see we have crawling all over this particular table, especially with metal bits down here. And if we were to enable primary ray bias at 1, those issues go away completely. So now with just a little bit of finagling, we now have a far better performing geometry all in all. And now, from this particular angle, at this particular resolution, we are finally running at a rock solid 50 FPS, meaning we are hitting our target frame rate because we are now running at 20 milliseconds as opposed to 85. We're almost running at 50 when we have refraction enabled, but I think at this point it's time for us to move on. So this is more or less how you work with optimizing your ray tracing. You will then take all these console commands and just tie them into your level blueprint at begin play using execute console commands. Optionally, you could also make a blueprint, which I prefer to do, where you can just have interactive custom events allowing you to, with the click of a button, toggle particular render effects on and off. For instance, ambient occlusion, translucency, refraction, and so on and so forth, allowing you to quickly fine-tune your RTX experience for a particular set or environment. All right. The last thing we're going to do is looking at optimization in a scene which is not using ray tracing, but is in general performing pretty poorly. So we're going to go ahead and turn ray tracing off again, and we're going to restart our project. And we're going to jump into Bad Studio instead. This is sort of an imaginary use case where we're going to look at what happens if you receive a set, possibly from a third-party vendor, which simply does not perform up to snuff. Before we dig into that though, I realize we quickly need to cover video playback, so let's go ahead and do that first. Just because it ties into a lot of the things we talked about today, especially in regards to media input feeds. It is always preferable to use other sources than Aja input for media if we can do so. But in order to do that, we need to know which are the good formats to use, what is the ideal workflow, how do we go about doing that. So, first of all, there's multiple ways of inputting media within Pixeltope. If you are not doing it via Aja, then you can of course use the media framework within Unreal. The ways we can go about inputting media is generally either through streamed media over Ethernet or local area network, or as video files, either as typical video files, MP4s or hop encoded MP4s, or any other media file that Unreal is going to accept, or as image sequences of raw EXR files or PNG files or any other format that Unreal supports. Let's go ahead and jump into an empty level and take a look at those different formats right now. Let's just jump back into our dev level just because it's nice and empty and more prone to be reliable than this horribly performing set. That is going to be our light examples that we light showcase. Terrific. Okay. So we are going to be looking at media playback. Let's get these, let's actually just move up above our set and add a screen so we can look at the media as we play it back. This plane is going to act as our virtual monitor. So let's go ahead and make it 16 by 9, 1.6 by 0.9. Let's go ahead and scale it up. Yeah, scale it up like so. Let's shuffle it over to the back. And now we're going to play back media. We are going to be looking at a few different kinds of media today. We are going to be looking at, let's go to media source, media source. We are going to be looking at media source regular video. We are going to be looking at media source experimental HAP. And we are going to be looking at media source image sequence. Okay, terrific. We're also going to go ahead. So we're now just going to build a quick media player from scratch, just so we have something to interact with. We are not going to make a custom material. We are just going to go ahead and use the built-in media video component within Pixeltope, simply because it gives us better visual results in that our video doesn't get destroyed by temporal aliasing within Unreal. We are then going to go ahead and go to media and create a media player to actually play back our different media sources. We're going to call it MP video player. And it's going to output the actual video to a media texture, which we can use on surfaces, called media texture video result. There we go. So we are going to take this media texture and put that on our surface plane. And we are now going to go ahead and add a regular video. So we open the media source, regular video. We are going to find the Pixelpalooza scissor reel. And we can actually go ahead and test that right now by just simulating our game or environment. Actually, you know what? I'm probably going to have to select our media video component and turn off use unjittered projection. There we go. Simply because with this enabled, the projection will not be correct. There we go. Then we can now jump into Preview Live. We can open our media player. We can start playing the video we just created. Yeah. And as we can see, nothing is currently playing back, which is a bit unfortunate. The reason for that is I never actually enabled use debug texture, which means we didn't tell the media video component to use this particular texture. So let's enable this checkbox, play it again. Play our video file from start. And we can see it's playing back as intended, looking nice and beautiful. Okay, so now we are going to test some logic, because the important thing here with video playback is that different media formats and media types have different amounts of flexibility in terms of how you can play back the video, seek the video, rewind the video, and so on. We're going to make a quick blueprint. VP video playback. We're going to go ahead and add a media source within this blueprint as a variable. Sorry, a video player. The media player is going to be the media player we just created, like so. And the first thing we always are going to want to do and begin play is start playing our video source. So we are also going to need a video source variable here. File media source, file save. We're going to use the more advanced open node, open source with options, which is going to allow us to right-click the options, split the struct pin, and set it to force autoplay and looping when the media opens. The media is going to be our video source, which we can just hook up here into the video source. We're going to make this a variable, which is public, so we can change it on the fly. Then we're going to make two custom nodes, px fast forward or FFV, as well as, actually, you know what? I was going to make a custom event for rewind, but we don't actually need that. We can simply make a function called px play rate. Then we're going to have a public variable for play rate, which is going to be a float. There we go. Compile it, save it, give it a default value of 1. And this is simply going to plug into the video player, set rate or play rate every time we trigger this custom function. and the play rate is going to be whatever this variable is currently set to. Then we just need to ensure that this variable is public so we can change it on the fly. We're going to ensure that this custom event is exposed to the editor so I don't have to make a control panel widget for it. And now we're off to the races and we can test our logic. We're going to go ahead and pull our video playback blueprint into the level. We're going to go ahead and go to the details panel of this particular blueprint and populate it with some data. We're going to start with our regular video file source with a play rate of 1, and we're going to go ahead and hit preview live. As you can see, it starts playing just like that. Now, if I were to say set the play rate to 2 and hit PX play rate, please make sure that you're watching the webcam feed on my side here, which is hopefully a lot smoother than the screen share down below. Notice that as I set the play rate to 2, the video is still playing perfectly fine with a play rate of 2. If I go ahead and set the play rate to 3, the video is still playing perfectly smooth at 3 times the speed. If I go ahead and set the video play rate to 4, however, things break apart completely. Whether it's due to the compression on the file, the size and frame rate of the file, or whatever else, we can see that the playback has just completely stopped. And it would not surprise me if Unreal is actually now about to tank, mainly because I was messing around with video playback at high rates while Unreal was still compiling shaders due to me disabling ray tracing. Let's give this half a second or so to resolve while I close some software in the background, and then we are going to go ahead and kill it if it doesn't return on its own. Let us just go ahead and nuke the engine. It might seem a bit callous not to give Unreal time to recover, but that's showbiz. Okay, so let's jump back into our level. I don't remember what I called it. It probably was Light Showcase. Let's launch it in the editor and see what happens. You can see that we are running out of time, so let's pick up the pace a little bit as well. Okay. There we go. Now, all our logic should still be where we neatly left it. Let's dismiss this. Let's preview live. Let's try one more time to see what playback looks like with this set to a play rate of 4. And let's just hope for the best. As you can see, this is what I was expecting. Still, the play rate is correct, but it's just skipping frames. We are seeing a slideshow, and this is not due to the latency of the video feed, but, well, the stream you guys are seeing, but it's actually just not performing as expected within Pixeldope. So you can see that we are basically capped at a play rate of fast forward at 3. I really should let it finish compiling shaders. The most likely reason for this limitation is because we are trying to play back an H.264 encoded MP4 file, which is running at 30 FPS full HD. That means there is a certain amount of decoding that has to happen on the video on the fly. Okay. I'm just going to bring this up and let it finish compiling shaders before we move on. Okay. And this also has other implications. Most typically used video formats today are encoded and compressed in a way where we have certain keyframes on regular intervals, and the rest of the data in the video file is stored as the difference on a particular point in time as compared to the previous keyframe. I'm sorry if my terminology is not correct here, but that is more or less the overall logic here at hand. You probably have seen these. You probably have seen what happens, for instance, when we miss a keyframe during playback of video, where everything suddenly turns to this sort of Lovecraftian mush, which is what happens when the video keeps playing. We keep seeing the difference applied, but we miss the previous keyframe. This also means that we can't really rewind in an effective way, because then you're going to see the difference frames are being applied before you actually get to the keyframe. So a lot of typical video formats are not very receptive to being played in reverse. If I were to try to play this video file backwards, so we're going to play, we select the video handler. We set the play rate to -1 and try to play that instead. I'm actually shocked by how slow this shader compilation is going. Very strange. We can see that we see the same slideshow as we just witnessed. I'm just going to stop it before it takes down my engine because we still combine shaders, but basically it's simply not useful. Other limitations of using linear traditional video files is that it's hard to seek in them. It's hard to jump to an exact frame, which means that having logic where maybe you need to jump to frame 512 and play from that particular frame in order to have lip sync is not going to be reliable using these video files. You're going to continuously miss by a frame or two, things are going to drop out of sync, there's going to be variable loading times, and they're just not going to be ideal for any kind of media playback operation that requires precision. Of course, with audio, you could, the audio is going to start playing back within Pixeltope as the video starts playing back. So if you're outputting audio from Pixeltope, that might not have to be the end of the world. But luckily, there's other options as well. We can, for instance, instead of using video files, we can use image sequences. So we do have an image sequence at hand here, which is just, in this case, going to be, I'm going to set to 30 FPS. And this is going to be a sequence of compressed PNG files. As you can see here, we have a sequence of image frames, and that's what I'm going to go ahead and open using my image sequence media source. It's worth mentioning that these are not raw EXR files, which would perform even better in a live playback scenario. Let's just go ahead and pull that into my scene, into my blueprint, sorry. I'm just going to drag it in here as my media source for now, compile it, save it, play it. So what we're looking at right now is individual frames as separate files being streamed into Pixeltope instead of a video source. So let's do the same test. Let's set the play rate to 2. You can see it plays perfectly. Set the play rate to 3. Still no sweat. Let's set it to 4, where the MP4 broke down completely previously. Not a hurdle whatsoever. Let's set it to 40. Now, of course, it looks like bogus, but it's still playing back incredibly smoothly. Let's set it to 400. Again, at this point, we are playing back so fast that nothing really makes sense anymore. But the playback is perfectly correct and doesn't break no matter what you set the play rate to. If I make logic where I need to jump to specific points of time within my video, then I can set to jump to a particular frame, and it's going to work with no headache because we are just jumping to a particular image file within our image sequence. If I wish to start playing back in reverse, this also is no headache whatsoever. It plays back perfectly both ways. So as you can see, using image sequences offers unparalleled freedom within media playback within Pixeltope. The last thing we're going to take a quick gander at is going to be HAP. in order to use HAP files which are still have experimental support within Unreal, we're going to have to enable a new plugin. We're also going to have to ensure that non-standard codecs as well as hardware accelerated video decoding is enabled within media playback within our project. Enabling these settings would probably also improve the behavior of our MP4 playback that we just were looking at. Just so you keep that in mind. If you have to use MP4s, you might want to be leaving these checkboxes enabled. We are also going to enable low latency, which is going to prioritize playback timing and speed over visual quality of the actual media. Then we're going to go to our plugin settings and we're going to search for HAP, go to built-in, and we're going to enable HAP media. That's going to necessitate a restart of our engine. And we're going to go ahead and try to play back a HAP movie file. Now, one of the most interesting parts of HAP movie files to me is the fact that they allow you to embed alpha within your movie file. This means that if, for instance, you have a pre-recorded green screen session, then you could actually package both your key and your fill within a single movie file and play it back later within Pixeltope. This means that you wouldn't have to worry about having a separate video file for key and fill, which means that you won't have to worry about keeping these two separate video files in sync. Now, there's good odds that this is not going to work. It's been a while since we tested this, but let's just hope for the best. And let's plug in our experimental HAP media source. Let's also point this at the file in question, which is going to be this haptest.mov file. And let's hit preview live with visually disabled. That is not a happy movie file because, of course, I changed my blueprint logic to not use the variable video source. There we go. Just hook that back up in the blueprint and hit play. And that crashed. Let's take a look here. Okay. So it might be something in the file, might be something with the current implementation of HAP. So I think for now, we are just going to move on instead of trying to debug why that did not play back as intended. Let's see here. Actually, there's one thing we can try before we give up completely. Let's dive back into our scene. Let's go ahead and open our media player. Let's try to forcefully open our HAP video file. Let's give this a second here. Interesting. There we go. Experimental HAP with a big E. And there we go. Okay, so on that note, let's just shuffle on. If you're interested though in using HAP files, we do recommend you check out the official notes within the Unreal documentation, which has a few interesting tidbits about the current implementation as well as what is about to come. All right, so the last thing we're going to do is dive into our Virtual Studio BAD, or let's see, BAD Studio, there we go, and look at optimization. So the use case here is, or what we're going to simulate here is, it's Friday morning. You were supposed to go live in 8 hours with a virtual set that you received from a third-party vendor. You've been handed an Unreal project file. And as you open it, you realize you have some work ahead of you. This set is supposed to be used again in a few hours, which means it's going to be our task to ensure that it's running rock solid at 50 frames per second. So let's go ahead and very carefully see what we have in here. There's no ray tracing active, but if we bring up our unit graph, we can see that we are currently, as we pull out, we're currently not rendering at 60 FPS. As a matter of fact, if I am to save this position, right now we are running at 130 milliseconds, and I believe if I full screen this, I'm either going to flat out crash or we're going to see a rather unacceptable frame rate. So I full screen this, and we are currently using 150 milliseconds per frame, and our budget is 20. So it means we are some distance off. The first thing we're going to do is check our world settings, and we can see that ViewSig is enabled, which is going to be the first thing we're going to kill. Hitting Control-Shift, we can also see that very clearly here in the GPU visualizer, because we can see Scene Capture Track Camera, which tells us that we are rendering the scene more times than, strictly speaking, is necessary. So let's go ahead and disable ViewSig. Let's save that. Let's look back into our camera and full screen again. So now we're down from 150 to 132. That's a big step forward. Let's look again. So first of all, you can see that the only bottleneck right now is GPU. This tells us that there's no blueprints causing mayhem. There's nothing bothering us in the draw thread, so we don't have too many draw calls or too many unique materials or anything like that. It's just there's too much work for the GPU to handle. If I was seeing issues in the game thread, if this was the bottleneck, then I would probably start looking at blueprints and what's happening in the blueprint calls. I would probably start doing a log dump of what's happening in the game thread. But that would be a much more technically complex and less interesting debug session to look at. And it's also going to be a much rarer use case. It's almost always, from my experience, the GPU that lags behind. So we can see here we have three big chunks. We have two planar reflection actors eating up a significant 20 milliseconds each, as well as the shadow depths dump here eating up 43 milliseconds. This tells us that, first of all, we have too many planar reflection actors, and we also probably have dynamic lights and not baked lights. So first off, we can see that we have a planar reflection actor down here on the floor lower level. We actually have three planar reflection actors, not just two. You can see this one is up on the stage. This one is down on the lower floor. And this last one is up on the upper position. So what I'm going to do is I'm going to take the lower one on the actual concrete floor, and I'm going to go ahead and delete it. On the lower floor, we could use screen space reflections instead, which I might actually go ahead and enable right away. We're going to search for a post-process handler. We're going to look up screen space reflections. And we're just going to go ahead and enable that 100% quality right away, so we still have that nice contact reflection from this orange highlight. I'm then also going to re-enable the lower planar reflection actor because I like having nice crisp reflections for our talent position. And for the upper planar reflection actor, I'm going to set this to be, I'm not going to delete it, we might need it. I'm simply going to scroll down and set it to be not, let's see, let's enable it and turn off visible. So the actor still exists, but it's not actually doing anything. The reason I'm doing this is we might later want to add logic to the planar reflection actors when we animate the podium from the lower position to the upper position, allowing us to toggle between these two planar reflections for planar reflection upper and planar reflection lower. Or more likely, we could also delete the upper reflection and simply parent this planar reflection actor to our camera root. So when we animate up the podium, the planar reflection actor will simply follow with. So now let's snap back to our debug position and take a look. So good news is we are now down to 119 milliseconds. And the biggest chunk right now is our shadow depths. So that's the next thing we're going to deal with. We can see here that all the light sources, which are supposed to be baked, have been made movable due to the orange dot. So we're going to go ahead and set all of these. You can actually just go ahead and search for light. And we're going to go ahead and work our way down and set these to be static. If this was a set we had just removed with no light bake setup done previously, I might also have to go in and generate light map UVs for our geometries. Luckily, in this particular case, that is not going to be necessary. So we're just going to go ahead and set all these lights to be static. Perfect. With this done, we can save our scene. We can just go to build and do a low quality preview build. Just to make this tick along as fast as possible, I'm going to scroll down to our light mask settings, and I'm going to drastically lower the amount of bounces on all our light sources. And then we're going to go ahead and build lighting only. Now we notice that nothing happens. We do a light bake and just there's nothing really happening. This is because force no pre-computed lighting has been enabled underneath light mask, which means that whoever built this set forcefully said that we are never going to bake lights. We actually have to turn this checkbox off to allow Unreal to do a light bake. Now we will trigger this again. It's going to start a light bake, it's going to gather the geometry, and now our light bake is proceeding as intended, as expected. We can go ahead and open our light swarm, where we should be seeing our bake being distributed across our multiple render engines, which we are not currently seeing, which is a shame. But we're just going to let this tick on while we keep looking around in our scene. There's nothing stopping us from just leaving this running while we keep trying to profile what's going on here. Next thing we're going to do is take a look at our overall geometry. If we hit Ctrl-Shift, comma again, we can see that we are using significant amount of time on our base pass. And if we hit Alt-2, we see something very interesting. Our wireframe looks absolutely insane. Every surface within this set has incredibly dense topology, which clearly is not necessary. We can see from this sort of weird triangulated wireframe that this looks to be using tessellation, which is a shader effect within Unreal. Tessellation is basically dynamic subdivision of geometry used for instance, if you have a planar surface which you want to look like cobblestone or brick, then you can tessellate that surface and do vertex displacement to give it a bumpy cobblestone or brick look. But there's no point in tessellating every surface, especially not uniformly and not based on camera position. We're going to go ahead and select any material instance which is exhibiting this behavior, for instance, the floor. Taking a look at the parameters in this material instance, there's nothing here that points towards tessellation, except this one, tessellation steps. This has not been input. There's not been an override for this material instance, which tells us that this value is input in the parent, which is the master shader, and this value is set to 64 tessellation steps, which is rather insane. So we're going to go ahead and open the master, the parent shader, the m_mrao master, which is being used by pretty much every shader within this scene. If we right-click the shader and open the reference viewer, we can see it's being used by pretty much every material instance within this project. We're going to go ahead and look for the tessellation input, and we can see that somebody has input a 64 multiplier. As you can see on this sphere, that is giving us pretty bad results. Well, we can't see it here because it's compiling shaders, but nevertheless, we're going to go ahead and set that value to 0, and we're going to save it. Let's go ahead and hope for the best here. Might be a bit gung-ho to do both lighting bake and trying to recompile our master shader at the same time, but I'm feeling lucky. What do you think, Magnus? Was this a mistake? No, I'm sure it's going to be just fine. Given that this is a master shader, that means we are going to be spending some time compiling it because it's also going to be compiling all its children and variations thereof. But now that it is done, we can go ahead and hit Alt-2. And we can see that this insane density has now gone away. At least in some regions, whereas others are still as lag-inducing as ever. When trying to identify which materials is currently tanking your frame rate, there's another useful menu as well, which you can localize underneath Lit, or this drop down here, optimization view modes. When it comes to lights, if we earlier had enabled light complexity, we would be able to see how many overlapping lights we have, which obviously is very bad for performance. We're going to take a look at that later, just so we have it covered. But we also have the shader complexity overview. This is going to kick in as soon as we're done compiling our last shaders. You can see that our light bake has also finished, which is great news. We see we have some geometries which have overlapping light map UVs, but it's just by a few percent, so I'm not too concerned. So when we go to light map density shows us that we have a nice uniform distribution of light maps. And if we go to optimization view modes, light complexity, we can see that the only place we currently have any dynamic lights is center stage. See, nowhere else do we actually have any dynamic lights being rendered. It's only here in the center stage, and it's not too bad. We have maybe 2 or 3 overlapping light sources, which is not too extravagant. Now, if we were to snap back to our start position, we can see that we are now down from 111 milliseconds to 43, which is 47, which is much better. We're still some distance away from 20 milliseconds, but we are almost there. Now, if I were to hit Control-Shift, comma one more time, we can see that the biggest chunk is the base pass, which means it's either material, geometry, or combination thereof. The base pass is basically the drawing of all the different objects within our scene. Sadly, we have no more information from the Profile GPU utility, so let's start trying to look in other ways. Let's take a look at our buffer visualization, optimization view mode, shader complexity as such. So we can see here that most of our surfaces are now green. All of these would have been red before due to the tessellation. We can see we have some red here on the side where we have the glowing bars, our composite plane, and our glass, but that's to be expected. Red is still not the end of the world. Bad is white or past white. But there's something rather funky happening over here, as well as over here on the glass here and these metal bars. Let's start by taking a look at this metal fixture on the side. So you can see here that the parent for this shader is another MRAO shader, which still has the same tessellation applied because it's a separate master. The reason we identified this so quickly was using shader complexity, where it was absolutely freaking out, telling us that there's something going on. You can also see it from Alt-2, the wireframe mode, where we can see that it's clearly being tessellated to not so great effect. So we'll do the same thing here. We just remove the tessellation node. We'll compile the shader. And just like that, as soon as this finishes, we will see this wireframe no longer be as dense as it just was. And we're going to be able to, there we go, we can see the density has been reduced. And at this point, our performance is even better. We're actually now down to 20 milliseconds. And this is despite still being compiling some leftover shaders. Now, in order to see our actual performance, we need to turn off genlock, because right now we can never have a performance better than 20 milliseconds due to the video output format. So what we can do right now is go to our setup tab in Director, go to routing, and we can actually just kill all our input and output routing. The reason we're doing this is now we're no longer getting any kind of reference signal. And as soon as the video pipeline updates, we can see here that, of course, our video pipeline has gone away. Let's give this a second. There we go. And now we are no longer constricted by the genlock signal and the video pipeline. But we can see we actually now bounced up to 37 milliseconds as soon as the shaders finish compiling. This is rather worrisome. You can see our screen space reflections are pretty high resolution, but quality 4 is pretty high, but that's not too worrisome. So there's nothing in the profile GPU that gives us anything to work with. But at this point, we're just going to have to feel our way to figure out what the last scenario is. Something that's interesting is that if we look this way, we are currently running at 10 milliseconds. As we start looking over here, we are currently running at 40 milliseconds because there's obviously more stuff in the scene. As we keep moving over, looking at time position, we are running at 16 milliseconds. And as we pan over here, our performance skydives to 80 milliseconds, which is completely unacceptable. Moving over here, we can see that there's nothing on the stairs doing this. Looking down here, the performance is still good. Looking at the glass table, performance is still good. But looking at this brick wall, we are having a very, very bad time. So let's go ahead and select this wall and try to identify what's going on. Something that's interesting is that on this side, performance is good, but looking the other way, performance starts diving. As we start looking at the geometry, we notice that there's two materials for this sidewall. There's this one for the right side and this one for the left side. That's this shader here. Something that's interesting about this handy looking slab material is that it looks rather nice. It shades gorgeously, looks like photorealistic rock, but it's actually a flat surface. This entire surface is actually an illusion which is brought into life using tessellation. No, sorry, not using tessellation, using parallax. If we were to zoom in closely, we can actually see the individual parallax layers for each individual slab. Parallax is a great way to have effects like this where you don't have to build geometry. It's all just using optical illusions based on vertex displacement. So let's compare the shader for the left and the right side. Obviously, somebody has messed with parameters on the left-hand side, and after a cursory glance, we can see that the right-hand side is using max steps for parallax at 32. And on the other side, this value is at 4096, which is a much higher value. If we open the shader, we can see that this value corresponds to the input here, max steps and shadow steps being used in this parallax occlusion mapping node. This is a node you're going to be seeing a lot, especially in assets bought from Megascans or the Real Marketplace. It's a great utility node to give you parallax occlusion, well, parallax mapping, but it also can be insanely performance consuming if you are using step values which are too high. The values we see here are completely unacceptable. We typically tend to use step values of like anywhere from 8 to 16. So 4096 is probably a bit too much on the high side of things. We're going to dip it down to 32, which is still a very high value for parallax, having 32 stepping values. And when this has been done, we can see that the performance on this side and on this side has been brought level. Because now we only have 32 layers for our parallax effect. And now, as we pull back into our nice full frame, we can see that we've gone from the start frame rate, which was about 145 milliseconds, to 16.2 milliseconds, which is well within our target budget frame rate, well, target millisecond budget of 20. If you want to keep optimizing, we might want to tone down the quality for our screen space reflections. We could go and bake the last few movable lights in a scene, or we could try to refine our planar reflection actor. But for now, we are in a good spot for our production later today. On that note, we've looked through how to optimize a scene, and we are done with today's session. Now, there's been a lot of information to take in, so I'm sure a lot of you have questions. It's currently 0:43 p.m. I think we're not going to wait as long as we usually do. So we are going to dip into questions and answers, and let's do 2 minutes. So let's reconvene at 7:45, and then we're going to go ahead and answer all your questions to the best of our ability. So we'll be seeing all of you in 2 minutes. Okay, so our 2 minutes have passed. We're gonna wait a few seconds to allow people to get back to their seats, and then we're gonna dive into the questions and answers. All right, so from the top, first question is in regards to the light swarm for light baking, which we just looked at. The question is, do you need a license for all the machines used with the swarm? The answer for that is no, absolutely not. The swarm is a standalone program running on your machines, so you're perfectly free to add as many as you want. There's no cap on that whatsoever in any way, shape, or form. Next question is, can you use multiple GPUs for baking, for instance, like in Octane? Sadly, light mass baking is currently CPU only. There's an experimental project on GPU light mass, which you can find here. Let me get the link. Okay, I can't actually copy that link, but we'll try to make the information available later. It's basically found underneath the Unreal Engine for document forums, where you can find an experimental project looking into using GPU lightmass. But there's currently no public stable version of using GPU. Next question. How much does the graphic interface use up CPU when it's running? And can you run it full-time when developing? What is the overall load? The graphical interface itself uses very little CPU. CPU in general is not really our bottleneck. In case you were thinking about the GPU, there's having the editor up and running, having the interface around the editor is going to take a few percent off of your overall performance, but it is really quite negligible. You can test this yourself if you have a dev build up and running by trying to run a scene in play mode within editor in full screen, and then trying to run the same scene in standalone live mode and simply compare your frame rates. You should find that they should be pretty similar, just with this separate standalone live mode being a few frames better in performance at best. Next question is there any issues using alphas with image sequences? My gut feeling there is to say no. I believe there's no issues using alphas with image sequences off the bat. But when I think about it, we've done productions in the past where we wanted to alpha out sections of a flipbook so we could have like free floating particles with the gradient alpha to the background floating around. And for some reason, we did not actually use the alpha channel for that. What we did is we made a simple script, batch script. So we had our alpha channel and our RGB data, and we actually just put it together on a single frame. So let's say that your image sequence is at 1024 video file. Then we would just end up with a final image, which would be the fill directly above the key. And then we would just make a shader that would just take the lower half, the key, offset it by 50%. And then we would use the black and white key to mask out the fill. Let's see, sadly, I don't think I have Photoshop on this machine, but I might have, let's see here. Unless Photoshop has shut it down, I might actually be able to use Photopea for this. Terrific. All right, so what we would do is we would just combine our fill and key like this. Let's go ahead and make a new project. That is just, oh, no, that is not what I want. Let's make it 1024 by 2048. The reason we're going to be looking at this is just in case, say that we don't have the option of using alpha, which might actually be the case simply because since we haven't used it in the past. So then let's say that this is going to be our image. I probably can't just, oh, there we go. Let's go ahead and scale this up. So if this is our fill, we would then simply have our key, offset it by, see, good heavens, I have not used this software enough. Okay, I'm going to drop this right now because the hotkeys here are not the same as in Photoshop, so this is going to be a lot of fumbling around. But basically, take your key, take your fill, layer one on top of the other, and use a shader to offset the key by 50%, and then combine these in a shader. As simple as that. Then you don't really have to worry about the alpha channel at all. I can show the shader as well. Let's go ahead and jump into our session. Let's go ahead and find a texture. And this will suffice. Okay, so we are just going to make a mock-up to fake the what you're basically going to be importing as your image sequence. So we're just going to stack the same image twice on top of each other as such. And this is going to be our texture. Okay, so if this is what your image sequence is, let's just pretend here that the top half is your key and the lower half is your fill. Now, then what you're going to need is you're going to need to offset your fill, offset your key up to overlap your fill. So you can actually do key fill combination and use that as your final output. To do this is a very simple bit of shader logic. We are simply going to need to, if we ignore this and just say that the image looks like this, we're going to need to do some very simple operations. We are first of all going to need to divide the height by 50%, which is going to be looking like this. Let's see here. Yeah, so when we do this, it's going to basically take our stacked images, divide it by half. So it's basically going to just fill our entire image with the top image, which currently is our key. The lower half, the fill, has now been offset out of the image by exactly one tile. So then we just need to have the copy of the same texture sample, or just we just need the same texture sample twice. And for the lower half, we are simply going to offset the image to get the lower half. So we're simply going to add to the UV coordinate half an offset. It's actually going to be a full offset in this case. So here on this side, we are now looking at the lower image. And since we're going to pretend this is the key, we are just going to use one channel. So we're going to pipe the key into our opacity and the RGB into our base color. And just like that, we have now combined the key and fill into the same image, and we are now able to combine it in the correct way. We can see here that our key is a bit faint, so we could simply see here. We can simply multiply up this to clamp it closer towards an acceptable key. And there we go. So from stacked image, we've now taken the lower half, we offset it up to overlap the top half, and we are using that to key the image. And this is what you could be using in your media playback material. I hope this made sense. If not, please reach out and we'll walk you through it with an actual correct image, which I sadly cannot create on this demo machine right now as I don't have access to Photoshop. All right, I think this has gone on long enough. I think we are going to wrap it up here. So before we hang up, next session is going to be covering studio setup from a technical perspective. We are going to be doing a deep dive into how to use our chroma keyer and how to set up a beautiful green screen from scratch. We're going to be looking more at all the pixel-specific actors in detail and how to use them from A to Z from a broadcast technician's point of view. And we're going to round off this first week and a half of Pixelpalooza with a multi-machine setups and how to operate them. So until next time, we hope you all stay indoors, stay safe, stay healthy, and we're looking forward to seeing all of you back again tomorrow. Thank you. Have a good day.